Learn how to use the Hardy-Weinberg equation to calculate allele frequencies from observable phenotype data. The Hardy-Weinberg equation is a fundamental tool in population genetics that helps us understand allele frequencies in populations. First, let's understand the Hardy-Weinberg equation and what it represents. The Hardy-Weinberg equation is p squared plus 2pq plus q squared equals 1. In this equation, p represents the frequency of the dominant allele, which we'll call A, and q represents the frequency of the recessive allele, which we'll call lowercase a. Since these are the only two alleles in our system, p plus q must equal 1. P squared represents the frequency of homozygous dominant individuals, 2pq represents heterozygous individuals, and q squared represents homozygous recessive individuals. The key insight is that we can directly observe the recessive phenotype. Only individuals with the genotype lowercase a will show the recessive phenotype. Both capital A, and capital A lowercase a show the dominant phenotype, so we can't distinguish them by observation alone. This means we can distinguish the recessive phenotype, but the dominant phenotype includes two different genotypes that look the same. Therefore, q squared equals the observed frequency of the recessive phenotype in the population. Now let's go through the step-by-step process to find allele frequencies. Step 1. Count the number of individuals showing the recessive phenotype in your population. Step 2. Calculate q squared by dividing the number of recessive individuals by the total population size. Step 3. Take the square root of q squared to find the frequency of the recessive allele q. Step 4. Calculate p by subtracting q from 1, since p plus q equals 1. Step 5. Verify your answer by checking that p plus q equals 1. Let's work through a concrete example to see this process in action. In a population of 1,000 pea plants, 160 have wrinkled seeds, which is the recessive phenotype. Here's a visual representation showing 840 plants with smooth seeds, the dominant phenotype, and 160 with wrinkled seeds, the recessive phenotype. Our goal is to find the frequencies of the S allele for smooth seeds and the S allele for wrinkled seeds. Let's start by finding q squared from our phenotype data. Q squared equals the number of wrinkled plants divided by the total number of plants. That's 160 divided by 1,000, which equals 0.16. This tells us that 16% of the population has the homozygous recessive genotype. Now we take the square root to find q. Q equals the square root of q squared, which is the square root of 0.16. The square root of 0.16 is 0.4. So the frequency of the recessive allele S is 0.4 or 40%. Next, we calculate the frequency of the dominant allele. P equals 1 minus q. 1 minus 0.4 equals 0.6. Therefore, the frequency of the dominant allele S is 0.6 or 60%. Let's verify our answer by checking if everything adds up correctly. First check. P plus q equals 0.6 plus 0.4, which equals 1.0. Check. Now let's verify with the full Hardy-Weinberg equation. Substituting our values. 0.6 squared plus 2 times 0.6 times 0.4 plus 0.4 squared. This equals 0.36 plus 0.48 plus 0.16, which equals 1.0. Perfect. We can also predict the expected frequencies of each genotype. Homozygous dominant SS equals p squared, which is 0.36 or 36%. Heterozygous SS equals 2pq, which is 0.48 or 48%. Homozygous recessive SS equals q squared, which is 0.16 or 16%. In our population of 1,000 plants, we expect 360 with genotype SS, 480 with genotype SS, and 160 with genotype SS. Let's summarize the key steps for using Hardy-Weinberg to find allele frequencies. Always start with the recessive phenotype frequency, which directly gives you q squared. Take the square root to get q, then calculate p as 1 minus q. Always verify that p plus q equals 1. You can then use p squared 2pq and q squared to predict genotype frequencies in the population. Remember, observable phenotype data gives you q squared, which leads to q, which leads to p. This is the pathway from what you can see to the underlying allele frequencies.